Hello, everybody. Welcome to today's webinar, Failures and Fixes for the Ford 6.4 Powerstroke. I am Amanda Harmoning, and I am an admin assistant here at AERA, and I will be moderating today's event. And joining me from the AERA team is Rob Monroe.
Hey everyone, Rob Monroe here. I look after membership and technical development over at AERA. If you're a member of AERA, there are grants and scholarships available through our Engine Rebuilders Educational Foundation. And we use this foundation to help with training in the field. We provide grants and scholarships for engine rebuilding, engine building, courses like, maybe one of your employees wants to take a welding course, or perhaps they want to, update some of their skills on some industrial machining or engine machining of some sort. We've got over $25,000 that we're giving away for 2020 for these scholarships. We've had excellent help from a lot of our suppliers. We've had we had a live auction that we did at PRI this year. We also did a live auction at the Rottler Open House this year. So again, this is a great opportunity if you're a member to help further yourself with some training. So take advantage of that. That is there for you. All right, well, let's get on with today's webinar, Failures and Fixes of the Ford 6.4 Powerstroke. And this is presented by Cass Choate of Choate Engineering Performance. Now, Cass has a well-known shop. It's out in Whiteville, Tennessee. And he is a specialist on the Ford Powerstroke engines and all Powerstroke engines. I know we, on the tech line, we bounce lots of things off of Cass and help get information from him all the time. And he's also got a service facility out there. It's called the Diesel Doctor of TN, as well as his shop's called Choate Engineering Performance. So it's a treat for us to have Cass on today, and he is going to discuss some of these issues we do see with the 6.4. So hey, Cass, how's it going?
It's going great, Rob. It's great to be here. I appreciate you having me. We really appreciate the AERA. They've done a lot for us as a business, and it's a great organization to be associated with. Tremendous amount of support. Some very bright minds working there, so it means a whole lot to us that y'all ask us to come and today and speak on behalf of the 6.4 liter, and that's the 6.4 is an engine that has been pretty well now the most hated Powerstroke platform known to man. It's been through a lot of changes of Powerstroke from the 7.3 to the 6.7 now. And obviously, a lot of the reasons for the changes were mandates because of the EPA. And we've seen the evolution of the Powerstroke engine. And this engine was only available from 2008 to 2010 in the Ford Powerstroke. However, it was extended longer in the international platform. But that has been a big part of our business, what we work on. We've kind of been known as the Powerstroke guys. That we do a tremendous amount of work with them, and even more so, the 6.4 guys kind of have adopted us and been really good to us, and have given us a lot of word of mouth business, and we're really thankful for that. So we've given a lot of attention to this platform. We've worked really hard with it to make some big changes and try to fix it permanently, and we've had really good success with it. So we've done a lot of things with the manufacturers and worked with them on some of the parts, and then we've gone on our own and developed some other parts. So today, let's take this time to kind of show you what I've seen over the course of the years on this engine. So the biggest issues that we have with the 6.4, and my mind works best, I guess, if I'm going to explain this, we'll just kind of start geographically. So we'll start from the bottom of the engine and kind of work our way up. Everybody can see my screen. This is not an uncommon picture for a lot of people that have 6.4 liters that have torn the engine down. This is obviously the main line with a spun bearing in it. It's not uncommon at all. The 6 liter did not have these kind of issues. The 6.4, you would see 6.0s that had spun mains, but it really was not as prone as the 6.4. And the reason, and there's several reasons for that. The reason why the biggest issue for the 6.4 with the main bore, the main bearing spinning, is simply because it has to deal with emissions. To understand the 6.4 liter engine, you really have to understand the emissions that are involved with that engine. I'll give you a brief synopsis of that really quick. So when they were making all the transitions, 2007, 2008 was coming on, They increased the level of specifications that they had for the emissions. So what they required, the mandate they required was much greater than that an EGR valve with a 6-liter could handle in an EGR cooler. So the number 7 and number 8 cylinder were actually let me stop there, maybe you hear me better. Okay, so the number 7 and number 8 cylinder on the exhaust stroke was used as a catalyst. The fuel was dumped in on the exhaust stroke, and it was used as a catalyst to help burn hydrocarbons off that had been accumulated in the diesel oxidation catalyst. Because that happened and everything took place in the engine instead of like the things that we see today, where you have selective catalyst reduction systems and things like that are after treatment systems that are dealing with the diesel exhaust fluids, all those things that are happening in the exhaust. All this was taking place as a catalyst and primer was taking place in the number 7, number 8 cylinder. So because of that, the diesel fuel was horrific on its effect of the cylinder wall. So we saw a lot of cylinder wall wear, a lot of thrust wear on the number 7, number 8 cylinders. Something else, that you see, and I always explain it this way: if you're spraying an injector, and the best example I can kind of give of that is if you were to stand at a wall, 10 feet away, and you took a shotgun, and you shot at the wall, and then you stepped back another 30 feet, and you shot again. The spray pattern is going to be completely different and much wider than what it was at 10 feet. So the injector being the shotgun and the wall being the piston, on the exhaust stroke, when it's actually spraying when it goes to clean the exhaust, the post-injection event that takes place, because the piston is so much lower in the bore, we see a lot of wall infringement with the spray pattern, and a lot of that fuel gets transferred into the oil. And because it does, it just wreaks havoc. Obviously, with the hydrodynamic wedge that the bearings are supporting the journal are compromised. There's nothing there for them anymore, and catastrophic failure occurs. But you can see in this picture this area that actually cleaned up. The reason why you're seeing it kind of shine up right there is there's a lot of distortion that actually happens. The bed plate design is fantastic design. It works really, really well for the 6.0s and 6.4s. It's much more robust. It's much more rigid than the predecessor with the 7.3 with the main caps. However, there is some things to keep in mind about that main line. One thing is the direction of rotation on the engine. You start to see a shift actually in the bed plate. And when you take this engine apart, if you were to mic it, put it back together, or you were to do just like this, line honed it, you'd notice that there were some shaded areas that it didn't touch off in the corners. And the reason why that is because that bed plate actually shifts, and it creates like an oblong, instead of the mainline bore being, instead of it being concentric to the axis that it runs, it's actually like an oblong shape, maybe at a 30-degree angle. So it starts to become distorted. The problem with that is, of course, we all know the bearing load. Now we've kind of got a side loading effect that's taking place on the bearing, and then the clearances also are compromised at that point, which we'll get into a little bit more. There's one other thing that we see, cause failures for spun bearings, amongst other things. But these are the biggest topics that I wanted to touch on today, and that is actually temperature related. Now we see this a lot more in the 6 liters than we do in the 6.4s. The reason why the 6.4s aren't as prone to this issue is because the 6-liter uses a hydraulically actuated, electronically controlled unit injector. So it's a HUE injection system, and the HUE injection system compresses the oil and uses that as a hydraulic to fire the injector. When you compress anything, you have the heat of compression that takes place. So because the friction that's inside the fluid, it actually starts to heat up a lot more. So those issues with the oil coolers stopping up, with the sediment that's in the block, all that's all issues that the 6.4 and the 6.0 both share. But again, the 6-liter, I see this problem more often with it than I do with the 6.4. So what happens is, as you can see, this standpipe here, it didn't take too well for the heat that was applied to it. So once that distortion happens, a lot of times what you'll do is you'll find a spun bearing and a rod. You'll pull it apart and you'll find out that there's some odd foreign plastic. Where did it come from? Because if it's a machine shop, you don't, unfortunately, it's kind of like being a detective. on a crime scene and it's been contaminated. You don't normally get to see everything. You're not the mechanic that necessarily takes everything apart, so you don't get to see the full crime scene for what it is. So you have to kind of be like Columbo and do a little bit of work and find out, what's going on and where it came from. So that tower right there, the problem is the filter now is on the outside, and when it melts, everything, obviously it has no filter to go through. Everything's pulled down the galley, and it gets in the journals and it just wreaks havoc and causes a lot of problems there. There's another thing that we see, spinning bearings. This is something that's not talked about because a lot of guys in the machine shop world, you're limited to, if that's all you do is bore the blocks and deck and hone, do all the machine work. Unfortunately, you might not be as privy to the information that might be concerning more along the lines of the vehicle itself or the truck itself. The 6-liter and the 6.4, they share a lot of commonalities. They're first cousins. The blocks look almost identical if you didn't know what to look for, except for the galleys for the high pressure oil rail and the bore geometry in the center of the block where the turbochargers went. You would think that it was the same block if you didn't do it every day. It did first glance. That being said, there are also some other parts that share a lot of commonalities, and one of those parts is a flex plate. Most guys are going to tell you it doesn't matter. A lot of this, unfortunately, is coming, from the customer side of it. When the block or the engine leaves your shop, everything's not done. It's not said and done. The failure, you think that you have consolidated, you've fixed everything, and the guy's not going to have any problem. That's not necessarily the case, because the guy still has to install the engine. And what he does between, the time you machined it or you built it, if you're an engine builder, the time he installs it, what he may do might be detrimental to it. So this is a big thing to look out for. Now, if you notice on the screen, you'll see there's 2 weights right here. The 2 weights are on a 6.4. There's a single weight on a 6-liter. We have had a lot of guys. Matter of fact, I can think of a couple of instances, and most of the stuff that I'm going to tell you today is just strictly experience, and I've probably got a horror story to go along with it that has either been an experience of a customer or we've had somebody. There was a truck that we had built an engine for, and they installed the engine. They shipped the truck back to us to let us look over everything, and when I drove the truck, instantly it had a horrible vibration in it. It was terrible, and we ran injector balance rates. Everything checked out. And I picked up on it right away. Some of the other guys, one of the other guys, I had him drive the truck, and he really couldn't tell a difference. But if you're around something every day, it's just the same way when you're over there listening to the cutter. If it changes speeds, if it's dull, you can hear everything because you're around it so much. The same way with this. But anyway, to them, it was okay. But what we wound up finding out was that they had taken, on a 6-liter and a 6.4, the transmissions are both 5R110W transmissions. They will interchange. One thing that will not interchange is the torque converter. The torque converter on one, the only difference is on one, it's an 8-bolt pattern. On the other, and that's a 6.4, on the 6.0, it uses a 6-bolt pattern. The big issue is on a 6-liter with one weight, if you take a 6.0 and swap it for a 6.4, there's 220 grams in difference in balance. That's a tremendous amount of weight. And it is a tremendous problem for bearings. With that much rotational imbalance, it definitely leads to spun bearings. We've personally experienced this with the truck that I was telling you about. If it's ran hard, very long period of time, and it has the wrong converter on, and that's what happened. The customer had the shop had put a different flex plate on it, slapped it back together, and then ran it. And then sent it to us when they couldn't figure out what was going on with it. So that is the main reasons that we see the main line, the main bearings spinning. Something moving along from the crankshaft. Now, there's something else I wanted to touch on for a second. We talked about the bore distortion and the issues that we were having with oil clearances. Now, 1 inch of bore to 1,000 clearance, pretty much the rule of thumb that we see on these. So you're looking on the main somewhere around 3,000 clearance, give or take a little. One thing that's a big issue, and I had a video, I just couldn't get it to upload, but I wanted to show it, but unfortunately it's not available to me. we have to grind every single crankshaft that comes through our facility, unless it was a Ford reman crankshaft. The reason being is on the number 2 and the number 4 journal, on the main journal, you will find that they're 2.5, 3 thousandths out. When you have that much total indicated run out, you start running into bearing clearance issues, or oil clearance issues, I should say, which become a clearance issue with the bearing if left untouched. So the number 2 and the number 4 journal, every single time, it's not 1 out of 5, it's not 1 out of 10. I would dare to say it was 98%, unless the crankshaft has been reworked by somebody before. So that's before we were doing any of our own machine work. Here's another horror story for you. I used to use somebody use several machine shops, and because of the trouble I was having getting the quality work that I was wanting and expecting, it forced us to do it ourselves. But the scenario was the same thing. The guy found the crankshaft that had run out. He said, it's bent, but we can fix it. They put it on a press to try to bend the crankshaft straight. They send it back to me. They check the journals. They're all straight. Everything looks good. I build the whole engine up. I go to put the front cover on. I rotate the engine over 180 degrees. No problem. I go to rotate it over the other 180 degrees. It won't budge. And the reason why is I had infringement of the snout because of where the fixture that they had the crankshaft placed on when they went to press it, it bent the snout up. And of course he was measuring the journals, so he thought everything was good, but he didn't realize where he was pressing against is what caused the problem. They're extremely hard crankshafts. So that reason we grind them straight instead of trying to bend them. And we've pulled engines apart that we've had 100,000+ miles on, and they generally, metal has memory. And once it gets to that place and it has that tweak to it, it will stay there for the rest of its life. And we've seen half a thou run out, after 100,000+ miles on it. That was the solution to that problem. The other things that we see a lot, it's just like this picture here that you can see, bent connecting rods. And a lot of that leads to, let me back up before I go into this just a second. One thing that I missed, we were talking about fuel dilution. That's a big issue, but that's not the only problem with fuel dilution as far as the emission systems are concerned. One of the biggest issues that we see, and this without doubt is the biggest, single most problematic thing that we see, and this is what led Rob to what I was telling you earlier, what I was going to be working on developing, is that the K16 pumps, some of the Ford reman pumps that we've seen out there, and not just Ford reman pumps, but reman pumps in general, the pumps tend to leak fuel into the crankcase. I have had trucks that were shipped here. I had a customer that had 52 quarts of diesel fuel that he drained out of the crankcase on his engine. The crankshaft was floating. I had another customer that went to 3 different shops after installing one of our engines and could not figure out. He had massive amounts of blow-by, he said, and he got smoke coming out the exhaust pipe. Couldn't figure it out. And I told the customer, I tell you what, you ship it to us. If it's anything, related to our engine, it's a problem, we'll take care of it 100% and cover the shipping. We'll cover everything. But obviously, if it's not, we'll diagnose it and we'll fix it and we'll go from there. And, the customer will take care of it. We did. Got the truck here. I walked past the truck while another tech was looking at it, and I was on the phone. I'm seeing it drip, fuel on the ground or oil on the ground. This thing was 26 quarts, 28 quarts, something like that of diesel fuel, and it's just running out of the crank. That's a major, major issue. So the injectors can leak fuel. One of the biggest issues with the 6.4s is everything's ran underneath the valve cover. It's kind of like a LB7 on a Duramax. They don't have that problem with 6.7 Powerstrokes because everything's external. But something to definitely be aware of is those fuel systems. The injector lines that guys are using, you can't reuse that. Once it's torqued, it causes the fitting itself to crimp, if you will, for lack of a better term, around the other part of the injector or the fitting that's going on the port, and it forms to that. Once you take it off, you put it back on, that form's broken, that seal's broken, so you can't do it. And a lot of guys run into those issues. So if you build an engine, you get it out the door, everything's good, everything's good, the guy comes back later, check his oil, make sure that there's not fuel in it, do a towel test on it. There's a lot of ways to find out if the guy's got this issue, but it will cost, it doesn't matter if you're John Causey, it doesn't matter who you are. When you build the engine, you're going to have definitely have a problem if that's the case. Well, moving along with with that, going into bent connecting rods, we see a lot of bent connecting rods. Powdered metal rods are fantastic for the application. They're terrible for one other application, or for one other reason, I should say. Most people think that the bent rods, when an engine has a rod issue, it's because it windowed a block. They generally take that as a sign of, yeah, my rod's broken. It's bad. It's windowed a block, something along those lines. When a rod's bent, most of the time, the customer, well, almost all the time, unless they come in with a low compression issue, will tell you there's nothing wrong. When you tear it down, you do a core inspection on it, you say, hey, you've got 8 bent rods, or you've got 4 bent rods, or a bent rod, or whatever it may be. They're going to say, well, wait a minute, it ran fine, except it had a massive amount of build out because of this failure. The thing that 6.4s are, again, have stacked against them, like stacking the deck against them, is power adders. Now, power adders, like performance tuners, not a bad thing so long as they're tuned correctly. And in some cases, I encourage it. But one of the biggest issues is guys that are pushing 32 plus degrees injection timing. And because of that, these rods, powder metal rods, if that had been a forged rod in this next picture that I show you, and this is what you'll see when you tear it down, obviously, you'll see the piston skirt that's possibly broken off of, depending on whether it's bend or twist or which direction it's bent. Here it is on a TN111. That's slight twist. It's not huge, but what will happen is as the rod bends like that, you'll start seeing marks in the cylinder wall like this before you take it apart, or once you disassemble it, you'll see what's going on. And at first glance, you might think, well, the previous installer didn't get the pin clip in correctly, and this is the result of it. It's not. The result of that is a bent connecting rod that side loads the rod. It blows the wrist pin clip out, and then it rakes up and down the cylinder wall and causes horrible, problems there. So getting back to the power adders, 30 degrees injection timing, these guys are running on these things, are tending to do 2 things, one of which is bending connecting rods. A powder metal rod, like I said, if it was a forged connecting rod, it most likely would have just snapped and the guy would have wound up buying a block. But with a PMR rod, it is they'll bend, they'll crumple, but they necessarily won't break. Under certain conditions, obviously they will, but a lot of times this is what you result into. This is the result of a bent connecting rod here. So you see that the pin boss, the area, the pad underneath there, it was contacting the crankshaft. And every time it would come down, it hit the counterweight and the crank. And typically what you'll see is this grooved area, if you can see with my cursor, the grooved area where the pin clip would go, you might not see it here. You may see it blown out over here. But what will wind up happening is that clip will just explode out of the piston. And the side, like I said, with that rod being bent, the side loading that takes place, it absolutely just destroys the pin boss area of the piston. Here's the other side of it where you can see that this guy that kept running this thing, it wouldn't have lasted much longer. It was almost ready to let loose. So this is another part of a piston failure. Obviously, everybody pretty much is very familiar with what causes this. An injector stuck open, it's just melted, and you can even see part of the ring right up there in the top of the piston. So injection failure, K16 pumps where water contamination that got into the fuel system that could have stuck the injector open would definitely result in that. There's another thing that high injection timing really causes as far as piston failure. So we see, and we have a lot of complaints with this. If you build 6.4s, if you've built them more than 2 days, you know what this is. This is a cracked piston, and you're very familiar with this because you've seen a lot of engines come in just like this. The guy's driving it down the road, no issues. All of a sudden, next thing he knows, at the next stoplight, he goes to accelerate off of, and I quote, "I wasn't beating on the truck. I was just driving to church on Sunday with a tailwind." Well, the problem with it is a misnomenclature. A lot of, and it's misnamed. A lot of folks refer to it as cracked piston. Well, you're seeing the result of something else that's going on. It did crack, but before it actually cracked, what happened with the piston was it burned a hole through it. This is a really good picture that gives a lot of information if we study it for a minute. One thing that you see is the rest of this piston right here in this area, it looks like a cracked rod. It's got a fingerprint, basically. You can see where it was fractured away from the mirrored image, the mirror surface of it. But right here in this image, you're seeing something completely different. And you're actually seeing a smoother area that is in this location. The reason why is because the reason why guys will say had no problem all of a sudden, I mean, it just, next thing I know, oil plugs on the side all blew out, and now I've got oil running down, the side of my truck, and I don't know what happened. Well, it's got excessive crankcase pressure because the piston wound up cracking all the way down. Now, the pinholes that develop in this area, the reason for them developing, this is what we refer to as a re-entrant style bowl. Again, with EPA and with emission standards being what they are, the auto ignition temperature of diesel fuels somewhere around 430 degrees. Auto ignition temperature of hydrocarbons is 700 plus degrees. So the hotter that we can get that bowl, the more we can burn the hydrocarbons off, the better the cleaner we can make our exhaust. So with this lip right here, basically as the gases are coming down, it makes this turn, and it's forced and directed back towards the center of the combustion bowl. When that happens, the reversal area, the reverse flow area is right here. The heat is going to dwell longer there because now instead of being able to exit rapidly, it actually has to speed up to go across this area right here on the side of this bowl. That creates a hot spot. And what you'll see, and what we've seen a lot of, is tiny, if you took a microscope, and you would have to take a microscope to see this because the naked eye a lot of times wouldn't see it, but if you were to look under a scope on this, you would see there's tiny pinholes that start to develop on some of those pistons. Next time you get a cracked a cracked piston in, and you've got something to examine it with, look really, really close in the pocket area and see if you don't see some tiny, tiny pinholes. Looks like casting, maybe a casting problem. A lot of the piston manufacturers get a bad rep saying, as far as the customers are concerned, they're worried about this area right here on a 6.0 is not there. This is a cavity for the oil, for the piston coolant jet to provide oil to go into and exit out the other side. A lot of folks thought that it was the actual casting issue that was causing that, because the area between where they make the cavity and the bowl itself, it actually was too thin in that area. That's not the case, but what winds up happening is if there's oil there and you've got a blowtorch that basically pierces through here, it can ignite that oil, and once it does, it literally just, it disintegrates that area. So that's a lot of the problems that we've seen with piston failure. What we do, here's another shot of it where you can see that smooth area that I was talking about. There's a lot of aftermarket vendors out there that do things with combustion bowls. This is an odd shaped one. That's the reason for the picture. But anyways, it's kind of proportionally awkward. This is a piston that we worked with developing through UEM, and this has a D-lipped area here. It's 2618, and it's for the 6.4 liter. It's a real low compression ratio, and it's a specific purpose that we developed that one. On our pistons, here you can see we'll machine the areas in the bowl to open that lip up. We machine the fly cuts or valve reliefs, whatever you want to call it, in there. But that allows for a lower compression ratio. It does alter some of the characteristics of the heat in the bowl, so it reduces the amount of fatigue that's placed in those pocket areas. So something else that we do when we machine these bowls, we make it a point that there are no sharp edges anywhere, because that heat typically is attracted to an area that it can't dissipate. It remains in that area. So the fillets that we use for the fly cut and the valve reliefs and the edges of the piston are all smoothed off. We call it like a G3 style piston. That's what we refer to it as. So something else that we use is a polyethylene coating. We've tried a bunch of different kind of coatings, and really did a lot of testing to try to find something that would hold up, that would withstand the cylinder temperatures and pressures of the diesel engine. And we tried numerous coatings, numerous different type of applications, and prepping for the piston. And this is what worked for us, and it's been doing a really good job. We're really happy with it. So that's the kind of the purpose and thought process behind the lip piston and the coated piston. Something else that we've seen on these are Ford remans. If you've been doing this very long, you've probably seen the spray weld technology that they use. Spray weld in its, application, if it's done correctly, obviously it's been done for years and years. It's fine, it's great, but I don't know if there was a preparation problem on the cylinder wall, but we've seen it consistently with the remans. That has been a tremendous amount of headache and problem for customers because obviously the second engine didn't last as long as the first. There's a picture of it. Let me back up. There's a picture here. You can start seeing it actually delaminate, for lack of a better term. Like I said, I don't know if it's in the preparation. I'm not a specialist in spray weld technology, but we've seen it get so bad to where it starts peeling off like this. It's a headache for any machinist because if you have a block that comes in, now one way to identify that block is generally in the reman facilities, not always, and it depends on where it was remanned at. They would put 2 slash marks between the bed plate and the block. I wished I had a picture of that. I didn't think to give it, but anyways, those slash marks indicate it's for reman, or it's a reman from whoever that's doing the spray weld technology. Anyways, this area right here, you can obviously see it peeling off and causing a problem. It's a headache. The machine stuff's extremely hard. That's what it looks like after the first pass. Your inserts don't like it, and it means for a long day. And if you're going to reuse that block, you've got to bore every hole. Some folks have been honing them and taking 10 thou out. I don't know if they've gone any further than that. It scares me to think that anybody would be honing that stuff, and I'm sure that there are people out there that have had success with it. I've just seen the effects of it. For that reason, I steer clear of it, and I don't want any part of it. We've got to get a 5-year, 100,000-mile warranty on our engine, so I want to sleep at night. I don't want to have any problems, and just knowing that and the effects of it. Like I say, we do other things and alter that. So some of the things that we do, as a side note, this is so what we do is we'll sleeve a block, unfortunately, when it comes in like that. For a lot of production engine rebuilders, it's probably not worth their time to do 8 sleeves in a block. It's way too labor intensive. It's not worth it. They'll just scrap it and get another block. For us, we have different applications for the block. So if we get a Ford block in there, or a block that has a spray weld on it, what we'll do is we'll generally set it aside and use it for a special purpose because we're going to invest a lot in that block. But this one here, this is kind of what started it all. This is a picture of an engine years ago that I built. We used another machine shop to do it. Yet another horror story for you. So the machine shop we sent it to, they went ahead and they punched the block. When they punched the block, they called me and he said, "Man, this thing is smoking like crazy. I thought there was oil in it, and there's not." Well, what he was talking about was that spray weld that was, and anybody that's cut into it, they're very familiar with it and they know. But anyway, he called me and said, "Man, this thing is smoking like crazy." And I told him, I said, "Well, if we need to get another block, we'll get another block." He said, No, I think I can. I'm gonna have to sleeve every hole, but I can fix that." Okay, that's great. So he gets me the engine back. I build the engine, and like I said, this has been many years ago, and I had back in the day when I didn't charge a customer anything up front. All my money was in the vehicles that I was working on, or the engines that I was building, ready to close on my house, and I'm sweating bullets, trying to get this thing done because I've got to have a big down payment on my house. And so I wound up putting this thing together. I cranked the engine over on first startup, and I hear it go, kind of have that little skip in it, that everybody's heard, that sends fear throughout the hearts of anybody that builds engine. And anyway, you start trying to make, you start grasping for straws. Well, maybe it's this, maybe it's that, maybe it's the oil pump's not primed up, maybe that's the noise that I'm hearing. It started up, and then I noticed white smoke. Maybe an injector, it's just hazing. Well, it was because they had low compression, because the sleeve was already slipping down. Well, it ran for a good 30 seconds, and I tapped the throttle. And as I tap the throttle, the piston comes up, the ring spread out, it pulls the sleeve that was installed. It's a straight wall sleeve. It pulls it straight to the block, destroys the block. Catastrophic failure. I got to pull the cab, pull the engine. Whole job has to be redone. There goes several days worth of work. So I called him and I said, "Man, you're never going to believe what happened." And I told him, I said, "A sleeve slipped and just slammed in the block." He goes, "It wasn't the number 7, was it?" "Yeah." "How'd you know?" He said, "I thought this might happen." That's the words you never want to hear at a machine shop, right? But he said, I thought this might happen. I said, what are you talking about? He said, well, when I machine the step for the sleeve, I got a little greedy and I machined a little too much off of it. Anyway, it was a lot of headache for me, but we worked through it and got past it, and that's what prompted me to start doing my own stuff. But that is the reason why we only use a flange sleeve. You can actually see in this picture where the sleeve is actually coming in and smacking the head. Let's see if I can, lost my place here. Rob, you still there?
Yep, still there.
Okay, good. All right, somehow or another I've lost my video here. Here we go. Wait for that to come up just a second. But that's one of the reasons why we only use a flange sleeve. And the flange sleeve, it provides, there we go. The flange sleeve provides a really good, like I said, it makes it very easy to sleep at night when you know that you're resting on the flange. But not only that, let me scroll down through here and find the picture that I wanted to show you. On higher horsepower builds, we've noticed that the decks are starting to crack when they've been pushed, and you start seeing some micro welding that's taking place and under the extreme cylinder pressures that the engine's under, and that deck will start to crack. Once the deck starts to crack, and basically it's headed straight for a water jacket. All my pictures are out of order now, but that's okay. When it pops up, I'll show it to you. So anyways, we started to use flange sleeves. The flange sleeve that we use specifically has a Rockwell hardness of 98, and that's extremely hard. It's not very fun to machine. It takes a good bit of time to do it because you really just can't push it too hard, too fast. So I apologize. There we go. There's a picture that I want to show you. So you can start seeing here pretty easy. You can start seeing some of the micro welding that's taking place, but also the crack that's gone in the block there. So with that being said, that thicker flange, which we actually don't, we have two different type flanges that we'll run. We'll run one for the repair, which is still a flange sleeve, and then for the high performance builds, we use a thicker because some of the guys are running C-ring setups, and we're seeing a lot of pressure placed in certain areas that can actually cause the flanges to break. So we switched to a different style flange sleeve that's a lot thicker. So anyways, that's been the cure for the problem. Moving along, you start seeing cylinder heads cracking. So we've got, as I scroll down, this is not a picture that is uncommon to many. A lot of guys have seen this. Almost every cylinder head that we pull off 6.4 liters tend to be cracked in certain areas. There's either between the glow plug hole, between the injector, the seats are always cracked. What we do is we work with another manufacturer, Civic. We use them for castings, and anyways, these are quality castings. They have held up really well. We've done a lot of testing. We've used them a lot. Here's a picture. And we also provide an O-ring. We'll machine a groove for the O-ring, and we'll place that. And it provides a good heat sink. So it basically reduces some of the cylinder pressures in that area because it is a heat sink, and it works well. We also do some coating as well, and that the coating that you see there, just like the piston, it basically is what we're trying to do is get the most thermomechanical advantage we can by less heat absorption through the surfaces. So those are definitely some things that have worked really well for us, and really glad to be working with them. One of the other issues out of the 6.4, and I'm going to start to slowly bring this thing to a close. One of the other big issues that we've seen has been catastrophic failure of the lifters, which the problem with this engine, among many, is that it was designed with the camshaft to be pulled out of the rear of the engine, not the front, which means on a 6.4, it's extremely tight. You've got to pull the cab to work on this thing. So if the camshaft has to come out, then in order for it to come out, the cab's coming off, the engine's coming out, it's a major ordeal. We see the lifter failures. The big issues for the lifter failures that we see are directly related to the amount of wear that we're seeing from the preload of the lifter. What winds up happening is we talked about the quality of oil being compromised. Because the quality of oil is compromised through fuel dilution and soot load, what happens is the 6 liter and the 6.4, again, they're basically first cousins in the way of blocks. Okay, they're extremely similar, but because the 6.0 had a HUE injection system that every time the injector fired, it sprayed oil on top of the tip of the rocker, it did not have oiling issues like the 6.4 does. The 6.4, unfortunately, when they came to redesign that block for high pressure common rail setup, because you had greater atomization through increased fuel pressures. So now instead of running maybe 22,000 psi pressure, fuel pressure, we could see 26,000 psi pressure. So the greater atomization, the smaller the molecule and droplet of fuel, it incinerated. It did not put off the amount of hydrocarbons as the other did. So because of that, moving and migrating from the HUE injection to the high pressure common rail, they kept everything else the same. The whole rocker assembly, it was changed, but it still was very similar in the design of the rocker. The only thing that they did different was they drilled a hole in the tip of the rocker itself. The oiling system didn't change either, but now you've reduced the majority of the oil that was in the valley, or excuse me, in the valve train area at the top of the head. About 40-50% of that actually came from the injectors after they fired. All that you've lost now half of the amount of oil that you had up in the valve train area, and so you would start seeing the valve bridges wear. You'd start seeing the rocker tips wear, and you'd have increased lash. As you had increased lash over time, now you've got the push rod that's just basically slamming down into the lifter, and the lifter now becomes a shock absorber. And once it detonates, basically it grenades, takes the camshaft out with it. So what we came up with and developed was something to fix that problem. Now this is a kind of a prototype picture, so don't pay attention to hardware. But anyways, this oiling system that we use is based very similar to the 6.7s, and it feeds off the turbo lines. I get a lot of questions from that. So this sprays down on top of the rockers. In this particular picture, the holes aren't drilled yet for it. But anyways, it sprays on top of the rocker arms, and it addresses that problem and fixes that problem. So anyways, we worked really, really hard to make the 6.4 a reliable platform. We've been able to do so, had really good success out of it. But it's not a bad engine, but like everything else, it definitely has its problems, and they have to be addressed. And you can't. It is not a very forgiving engine. What you can get away with 350 Chevrolet, it's not the same thing because it's not dealing with the same trials as the 6.4 is. But I appreciate the time that you've allowed me to come and speak, and if there's any questions, I'd be more than happy to answer them this time.
Super. No, thanks, Cass. That was a great presentation. It's funny you mentioned about these spray welded blocks. We get so many questions on the tech line, where machinists or members are starting to board those blocks, and they don't know what's going on. They don't realize it's spray welded, and they'll ask us. They'll go, what material is this block made out of? Or it's so we kind of chuckle because we're used to the question now, but they can tell because the sparks that are coming off and their poor cutters, they didn't make it halfway down the cylinder, and things are bad. So that was good that you addressed that for sure. Another question, Cass, that we get on the tech line quite a bit too is, what is the difference between that Max Force 7 and 6.4? I mean, I know the specifications are slightly different, but is there a difference in the piston there at all?
Yeah, there actually is. Like you said, the compression ratio is lower on the Max Force 7. The oil ring is different. We see a lot of questions about the in-gap clearances. Keep in mind the things that you'll find on Process Pro might be conflicting on a couple of areas with the ring gap clearances. That's because one is a Ford clearance, one is a international clearance. The Max Force 7 piston's a little thicker crown. It does not have that reentrant. It is a reentrant still, that bowl. The pictures that I showed on the presentation were actually a Max Force 7 pistons. That's the only piston that we use, but it starts life as a Max Force 7, then we machine it. But the Max Force 7 piston does have a different combustion bowl design. Like I said, the ring sizes are different. The casting thicknesses in certain areas are thicker as well. So there are definite differences between the two. But as far as a drop-in replacement, it'll drop in and suit your needs.
Okay, all right. Another question we have is, do the 6.4 engines have as many head gasket issues as the 6.0?
No, and that's a good thing. I'm glad you brought that up because I wanted to point it out and I forgot. The 6.4 doesn't have as many issues. Now, back in the day with the 6 liters, I think January 2006 was the production split. They went from 18 millimeter to a 20 millimeter dowel pin in the heads. And the reason why is they were trying to retool and kind of shifting towards that 6.4 block. Now, all your 6.4s, obviously, the dowel pins are the same and they're 20 millimeter because it uses a larger head bolt. The head bolt is not only does the actual major diameter of the bolt larger, the flange is much, much larger in area. So for that, there's more clamping surface, and that has eliminated the head gasket failure issues, not 100% because you don't never know 100% who you're dealing with. Under stock application, you rarely ever see a 6.4 head gasket blow. When you increase injection timing, that's just always going to bring a problem. So yeah, we've seen some failures of that. But what I did want to say is that the head studs, ARP studs, a lot of folks are talking about, I want to use bolts instead of studs because I'm afraid of the studs. I think they're just over tightening them and they're cracking the block. The truth of the matter is it has nothing to do with the stud. It has everything to do with the application. It doesn't have to do with the torque spec. But if care is not given to run the stud down and then back the stud off, and then preload, what we like to do is preload the nut on the stud and mark it with a paint pen to ensure that it doesn't get anywhere near bottoming out again. Because if you put any axial load on the block itself, down in the bolt hole instead of the threads, if it bottoms out, it's actually pulling against the threads and pushing against the bottom of the block, and that's where your crack develops. So it's key to make sure proper prep of the threads and proper installation of the stud.
Okay, all right. One other question we got, like in a 6.4 liter, any issues with the injector cups? Do you see anything that's an issue there?
Injector cups haven't really been an issue with either the 6.0 or the 6.4 because they went from the brass style cup of the 7.3, which we used to see split a lot. Rarely ever do you see any failures of the 6.4 cup. I don't know that I ever have. The 6 liters, obviously, the cups a lot of times were misdiagnosed because of the crack in the head, generally developing between, the number 3, number 5, the number 5 injector hole. And we would normally see a crack in that where you wind up having your coolant, your fuel mixing with your coolant. So no, not really any issue or any concern there.
Okay, all right. How about things? We got another question. What are your thoughts on like the DPF and EGR deletes? What effects does that have on the engine components?
Well, there's obviously the legal aspect of that, but strictly speaking, mechanically and how that would affect. Anytime that you can reduce, the truth of the matter is, anytime that you can reduce the soot load in the oil, which when you're doing exhaust gas recirculation, anybody that's ever pulled an intake or ever looked at the cylinder head of any engine that had an EGR on it, you obviously see the coating. Well, anytime that soot gets into the cylinder, it's going to be absorbed in the oil. It's going to be deposited. There's the reason why we have major differences between the oil that we used to run and the oil that we run now, because one is more anti-detergent. It's trying to, or a detergent oil that's trying to break this up, and one's more of an anti-wear, the zinc content. That gets into a whole other topic between the issues that the common oil has now and the purpose of that oil and the reason why it's used and the reason why it's designed, much of which revolves around the emissions. Trying to make sure that you're just constantly dispersing that soot load that's developing in the oil. The adverse effects of tuning, there are none so long as tuning is done correctly. That gets back to injection timing, fuel pulse width, exhaust gas temperatures, and cylinder pressures.
Okay, all right. We've got a question that's come in. Do fuel additives help increase lubricity in the fuel?
Yeah, definitely. Fuel additives, yeah, they're definitely depending on obviously the manufacturer. There's a lot of snake oil that's sold out there. We dealt with higher sulfur content in the fuel, and much of the failures that we see now are related to lack of lubricity in the fuel systems. But a lot of talk about that lately. Well, I say lately, 2011 to present, even Dodge switched over, or Fiat or whatever now you want to call it, but they switched over to a CP4 style pump, which has been a tremendous amount of. They actually have a class action lawsuit with Ford, I believe, and Chevrolet at this time with the CP4 failures. They were claiming that the lubricity content of the fuel based on a German soil was not the same as that of American soil. Our standards and their standards aren't the same. And that was much of the reason why. Personally, we looked really hard at re-engineering that pump and took it apart, did some testing on it, actually made some parts, and then decided it just never went to production. We never actually proceeded. But the reason why the CP4 failures, I know I'm chasing a rabbit on that, but that's such a big problem. I know somebody's out there listening that has had those issues with that. The reason why the CP4s fail, it's much like the same reason why it's the same scenario between a flat tappet lifter and a roller lifter. The flat tappet lifter, obviously, is rotating on a convex surface, whereas if the roller lifter ever had a chance to turn sideways, it would be all said and done. It's the exact same, pretty much the exact same setup that way. But anytime you can add a better lubrication to the fuel, it definitely, especially with these pumps running higher cylinder pressures and a lot more internal fatigue, definitely a good idea.
Okay, all right. What we're going to do, Cass, we do have a few more questions, but what I'm going to do is we'd like to try to cap our webinars off at about 1 hour because we respect everybody's time. We know you have to get busy in the shop and get to work. So what I'm going to do is I will pass the rest of the questions that we have off over to Cass, and he will get back to you with the rest of those questions in the next couple of days. So we'll do that for you. Cass, I just want to thank you. I mean, I know you're busy. You're always on the go, and we appreciate your time and you helping us with this today. You covered a lot of stuff, especially on the tech line. I mean, you answered a lot of the questions that we're getting all the time, and that's why I was pretty excited to have you come on and do this webinar for us. And I do respect your time, and I do appreciate it. So thank you very, very much.
Oh, I greatly enjoyed it, and I really appreciate it. I'm just glad to be any part of the ARA and do whatever I can to help. So thanks for asking.
Super. Yeah, no, thanks. I'm going to bring Amanda back on. We'll just kind of wind things down here for today, and she's going to talk to you about there's a survey and how you can contact us. So thanks again, Cass.
My pleasure.
All right. Thank you, everyone, for listening in today. When you leave the webinar today, you will have a survey pop up. Please take a moment, fill that out. Let us know how we're doing. If you have any additional questions for Cass, you can toss them in there, and we will get them to him. Also, watch out for a follow-up email tomorrow. This will contain a link to today's webinar. This is yours to use as you want. You can use it to watch if you got pulled out a couple times. You can use it to pass along to staff, colleagues, whatever you would like. It's yours to use as you wish. And lastly, you'll see our contact information is there. You can reach the AERA staff at 815-526-7600. And below you'll find my email along with Rob's, and Karen, who handles membership services, and Steve, who is our operations manager. Thanks again, everyone, and we hope you have a great rest of your day.